Hello and welcome back to Compiler Programming. Today I thought I would do something a bit different because I thought that the code is maybe quite unapproachable at the moment, and also even if you watched all of my videos, which I doubt anybody actually did, there are a lot of changes that were done between the videos, and especially lately I'm doing a lot of sort of internal architecture work on the compiler. And it's a bit hard to figure out what actually happens here, like where are all the ins and outs and how does the compilation actually happen. So today I thought I would kind of walk you through as to how mass compiler works, all the way from how it's built, how does it get in the source code, what happens afterwards, and so on and so forth. It's also important to say that this is sort of the current state of affairs. Things change quite a lot and nothing is really cemented in place. I constantly rip out and replace even kind of fundamental systems in the compiler, whether it is tokenization, overload resolution, I don't know how types work, what types are, and so on and so forth. So there's constantly flux of things, but this is sort of the state of the compiler at the end of July 2021. So let's get started. So what I have here is I have a batch file that I use for building the release version of the compiler on Windows. There's nothing really fancy here. There's some flags, nothing kind of out of the ordinary. The main thing here is that we are building the main CLI, which is called mass, and there is a bunch of optimizations flag. But if you notice, before the actual compiler is built, we build another file called meta.c, and then we run that file. So this is something that is definitely worth talking about, and we will get back to it at various points, I think. But the gist of this is that instead of defining data types in C headers like you would normally would, instead it looks something like this. So they are described in this meta program in C. Why would I do that? Well, for one, even for C, it helps generate certain helpers and helps the types to be more consistent. But more importantly, you notice that some types have this thing called expert compiler, and that makes those structs be automatically exposed to the user program when they are interacting with it, and we will see it a bit later. But yeah, so there is this whole metaprogramming part in C. I did a few videos on that, so you can kind of scroll through the playlist and find them, or I might link them in the description. But this program is compiled and run before we sort of start running the compiler itself. Okay, so now let's go to the CLI. So this is a very tiny wrapper CLI around the compiler. As you can see, the whole thing is what, 170 lines of code. And the usual things, it can show you the usage, it parses the arguments, nothing really fancy here. And the only really interesting part starts around here. So when we start executing, we first load something called SD prelude. Okay, what is that? Well, the compiler itself exposes very minimal set of things to the program. And so a lot of things that you would expect the language to have out of the box are actually defined in the language itself. So this is the prelude, and as you can see, there is a bunch of to-dos that are here for quite a while, but I'm still not sure what is the best way to handle them. But more to the point, as you can see, we have syntax definitions for what are if statements. So if expressions are currently part of the compiler, but if statements are not. And I'm not even sure I would keep if expressions as part of the compiler, but for now they are. Anyhow, so we also have things like while and for loop, which are also not part of the compiler, and how they work is actually quite interesting. So what this says here is that we will match on the while keyword, and there can be anything, and then we expect curly braces, which is how the while loop looked like. Then we defined some placeholder. We define two labels. One of them will point to here. This is a placeholder label. And we also tell what does break and continue actually mean for this loop, right? Because break is supposed to go to the loop end and continue is supposed to go to loop start. So pretty straightforward here. Then we have a condition, which is the condition of the while. And if the condition is successful, we execute the body and then we start from here. Seems pretty straightforward. For is more of the same, except that we also have this post thing in the body, and that actually is probably a bit broken because continue shouldn't go to loop start, it should go to here essentially. Yeah, it should go to here, so I'll actually add fix me. So sometimes it's nice to walk through the code to make sure that it actually does what you think it does. But yeah, so as you can see, for and while loops are defined in the language itself, as is debugger statement and even goto. Now goto is and debugger statements are interesting in that they just have these inline bytes, and these bytes are corresponding to the encoded assembly instructions, so machine code for x86-64 CPU. This is a int3 instruction, and this is a jump, and then we have a label here. Okay, then we define some types, and then there is this giant horrendous section, which will not really look at what exactly it does. The whole point is it generates overloads for various arithmetic types. So because you can have like U8 plus U8, U16 plus U16, and so on and so forth. So this is just a giant mess. I was just trying to push the compiler to the maximum. This is pretty funky stuff what's happening here. It seems to work okay-ish, except for occasional things, but I definitely need to think about how to make this nicer to deal with. Okay, next we have definitions of operators. So again, something that makes math quite nice and not unique, but certainly in a very small group of languages, is that it's possible to define arbitrary operators. And these operators sort of act as macros. As you can see, we don't specify types for x and y, and we just verbatim place them into the function parameters, and then the whole overload resolution just happens, and everything does what you expect it to do. But yeah, so we have operator definition. This is precedence of the operator, and then whether it is infix or suffix is inferred from how you write this. So this is a prefix operator, this is infix operator, and you can actually have suffix operators, which we don't have any, but I could easily do something like this, and then this is a suffix operator, right? Because the actual argument goes onto this side. Okay, I'm not going to talk about static sort yet, and this stuff is not really interesting. But the point is, before any of the user code runs, we parse and run this whole file. Okay, let's jump back to the CLI. This just tries to find the main entry point like you do in C, int main. In our code, this would be just main. And this is where the first interesting thing starts. So I could do two different things with the compiler. The first thing is I could compile FizzBuzz. So now it's compiled, and I can do build FizzBuzz, and it runs FizzBuzz. But another thing I could do is I could just straight away run the FizzBuzz. And when you run it, it is still compiled code. So it just in time compiles the code to native machine instructions and then immediately runs it. And this is this switch. So if we run, then we just, as I said, JIT the code and we try to find main and we just jump to it. This is technically not very nice and safe, but it is okay for now. Maybe later it will be a separate process. We'll see. Okay, and in case we compile, there is a bunch of stuff that has to do with where we're going to output it. That's not really interesting, but the interesting part is that we will write the executable. Okay, which executable are we going to write? Well, let's get back here. So we did go through this prelude file. Okay, so this stuff, this was all parsed, but not really executed. We'll see what that means a bit later. And then we try to load the actual file that the user passed to us. So for example, this fixtures FizzBuzz, and we are kind of actually importing it into the program. Okay, so let's go and look into import. So we are already here, and this is program import module. So what does this do? It sets up something called execution context, and this is an argument that is passed virtually to every function in the compiler that just holds the result of the compilation, whether it was success and error. It holds a current module, it holds the scope of the current execution, and a bunch of other important things. This sort of works around the fact that you cannot easily have sort of things that are available in every function in C, but yeah, so I have to pass it manually. Okay. Next is the interesting thing, that is program parse. Okay, so let's look at program parse. What does that do? Okay, well, it looks like it tokenizes things and then it calls token parse block. Okay, so let's quickly look at tokenization. Originally, I had a handwritten tokenizer, but it wasn't the fastest thing in the world. So now it is actually generated with something called re2c. It's a pretty fast compiler for, or tokenizer generator, I guess. Let's take a look here. So this is the project page. I think it has a website which is explains quite nicely. So if you want to look into exactly how it works and what it does, this is pretty good. But yeah, so this is a pretty standard tokenizer. We go through the code, we generate tokens for each thing in the code. So for example, this would be an identifier. This is actually also an identifier, but of a different type. It's an operator. We have parentheses and so on and so forth. Now we have strings, numbers, as you would expect. Now, one interesting thing about mass, which is distinguishes it from pretty much every other compiler, but Rust does it a similar way, is that when you have braces, they are actually tokenized in a nested way. So you have, as a tree, when you open a brace, you start sort of a level of the tree, a level node, and you have children of these, and if you have another braces, it's another level, and so on and so forth. So you get a tree of tokens instead of just getting a flat list like you might in many other compilers. This just makes some things easier. Some things are not great, but it is, I think, mostly positive change. So for now, I'm keeping it. Another interesting topic about tokenization is that since it is, the user can define any kind of operators, they are not actually hard-coded in the tokenizer, what is considered to be one operator. Instead, it is assumed that any symbols that are sort of joined together without a space is a single token. So this would be a single token, but if I add a space, then it's two tokens. I can also add like something like this, and this whole thing would still be a single operator. There are very few occasions where it's not super convenient, but I think overall it is perfectly fine, and I don't have too much trouble with this kind of stuff. But we'll see if this is gonna stay as it is. Okay, so we go through the tokenizer, we get our tree of tokens. Now we are ready to go back here and see what happens here. So we have token parse block, and then we have value force exact. This we'll get back to what force exact does. First, let's get to token parse block. Okay, this is token parse block. And in here it is mostly, again, what you would expect out of any parser. We go through the list of tokens. We figure out what we kind of try to match it to the next semicolon. But there is an interesting thing. Now, if we go back to the prelude, we have these syntax statement, and these are macros that are matching our statements. And this matching happens in here. We have this token matcher in scopes, and this goes through all of these definitions of syntax statements and tries to match them one by one. If it matches, then we will get back to this in a second. Then we sort of handle this statement. If not, we consider this to be an expression and we try to match an expression. And this is just a cleanup, nothing really interesting there. But if we matched a statement, something sort of interesting happens. So you see that there is this lazy value. And the way that works is a bit interesting. So Mass compiler is currently more or less two paths. In the first pass that happens here, we generate these lazy values. And lazy values are sort of, it's a giant built up closure or a thunk, I don't know what is the best terminology for it. Basically, it's a list of functions that when called will produce some machine code. And the reason we are not doing it right away, because we don't always know at the point of parsing what should be the location of each of the things. Let's look at something like, what can we look at? Well, let's open FizzBuzz and we'll look at a function. Right, so let's say we have, well, that's fine. We have something like this. I'm just thinking, is it the best way to explain why there is lazy stuff? Probably not. Let's instead look at this code. Right, this is a bit better. So we have a print function. This is a pretty stupid way to print integers, very inefficient, but that is fine. The point is, for example, if we look at this count variable, when we are parsing this sort of from left to right, right? We realize that this is a statement, we're creating a count variable, and you want to assign it to something, right? So at this particular point in the compiler, we have two problems. Problem number one, we have no idea what is the type of count. And number two, we also don't know where the count is going to be stored because we can't really allocate any memory because we don't know what the type of it is. So during the first pass of the compilation, we go through this block and we realize that the last statement of this block is this expression. This expression has basically the type S64, because literals are defaulted to be S64 unless you specify type something like this, then this becomes U16, but by default it's just S64. So it knows that the type of this expression is S64, and then this whole thing becomes a lazy value. And now we are ready to say that for the count, the type is actually S64. We will allocate right now on the stack, so we don't do register allocation. And we reserve space in the stack. And then another interesting thing happens. So once we finished doing the same thing for the rest of the body, we are ready to generate machine code. And this is where that, where was it? In program, parse, yeah. So the next thing is we have all these lazy values. We are ready to force them. So let's take a look at value force exact and what it does. So it creates something called expected result. And this is a pretty standard practice, I think. At least I saw it in different compilers as well. And the idea is that when you're generating instructions, it is very useful to know where the result of that instruction is supposed to be stored. So again, if I have something like, for example, something like this, right? We are doing 0 minus integer, so we're negating an integer. This is actually not even required. We could technically do this, but whatever. We are taking an integer, we are doing some operation on that integer, and then we are storing it back into an integer, into the same value. And it is very useful for compiler to realize that we are sort of overwriting one of the operands with the result of the operation because it can generate better code in this case. And this is what this expected result does. It is, it tells the lazy code where does the result of operation supposed to be placed into. And then we call this value force. Let's try to find, where is that? Yeah, so this is what it does. And the interesting part here is this, right? So there are lazy values in the compiler, and they're stored as sort of these lambdas, closures, whatever you want to call them. So they have a callback and some payload. Okay, let's look at one of the callbacks. Mass handle. So this is probably one of the most complicated ones, but that makes it also very nice to look at because it actually uses all of the features of the system to make things work. So as far as payload goes, it knows what was the operator, so plus, minus, so on. And it has two operands, so left-hand side and right-hand side of an expression. If we look at something like integer equals, it would be 0, integer, and we know that it's a minus operator. Okay, so what do we do? Well, we switch on the type of the operator, and then we are doing interesting things. So we check if both sides of the expression are actually constant values. Then we perform this operation right away. So if I have something like 0 minus 1, in this case, we know both operands of this, so we can just say that the result is going to be -1. So this is what this part does. And then we are starting to calculate the actual result. So first we allocate a register and force the expression that is the left-hand side into that register. So this value, I think it's worth definitely talking about this. So the compiler, even though it is written in C, is actually mostly a dynamically typed system. So the value can be pretty much anything in the system. You can put it in here, you can tag it with something called descriptor, which tells you what type it is, and then you can store anything you want in it, including lazy values. So we can check if something was already calculated, it will be a regular value, or we can check if it is a lazy value, and then we will force it in the same manner as we are looking at right now. So the whole process is recursive. Okay, so we take left-hand side, we force it into a particular register. We take right-hand side, we also force the result to be in a particular register. Then we figure out which x86-64 instructions we want to issue for the operation. In this case, we will have like sub, right? Because this is what we are doing. So 0 minus integer, this is a subtraction. So sub instruction. And we are doing this push eagerly encoded assembly. Okay, so what does that do? That goes into encoding.c. And we have this push eagerly encoded assembly. Okay, that looks kind of interesting. There is a bunch of checking here that is not really interesting, except for the fact that we are trying to find the specification that would tell us how to convert a human readable or more or less human readable instruction into something that the computer understands, which is the machine code. So if we go back here, this is more or less readable. So this would be like in reality sub. So we're saying subtract left-hand side and right-hand side. And by the convention, the result will be in left-hand side. Okay. So encoding match is this function, and it's a very dumb function, and it's very, very slow, and something that I will need to rewrite. It just linearly goes through the list of things and tries to find the matching encoding. It is a bit more tricky to actually make this fast than it might seem without exploding the memory. So we'll see. But the whole point is we have another file called instruction.c where I more or less manually copy-pasted the encodings from different instructions from this website that you might have seen if you watched other videos. So there is a Felix Clutia x86, and then there is the encoding. So I just take this and I copy paste the instruction, and I change this stuff to not contain special things like plus and so on, and use my own representation for it. But this is essentially these data just copied over to the compiler such that it can actually manipulate it. Okay, so these are the instructions. Let's get back to encoding. We have match, right? So we're trying to find the encoding. If we didn't find it, we report it to the user. If we did find, we are calling this function. Okay, so this whole thing is just what any assembler does. It's not really specific to mass compiler in any shape or form. It takes the takes the operands of the instructions, whether it is register, memory, and so on, and it converts it to machine code. I talked about it in other videos, and I said this is literally just a very, very simple assembler. So there is nothing particularly interesting about this, except for the fact that it happens very, very early in the compilation process, unlike any other compiler I know. So we encode instructions even before we know where they will be located in memory or how they sort of relate to each other. We just encode the bytes of the instructions. And this causes an interesting problem where, as I said, since we don't know where in memory they are located, if we have something like a goto, which is supposed to go from one instruction to a different instruction, we need to know how much to jump. Like if you saw assembly, it says like jump, I don't know, minus 16 or something like this, and which is the distance between those two labels. And so for that purpose, we have auxiliary instructions, which are called like label page. And we have another one, which is stack page, which probably deserves its own video because that one is really, really tricky. But yeah, so the most important thing to note here is that we convert instructions to bytes very, very early, immediately after we can. And then we add extra fake instructions to our instruction list that will tell us sort of where to patch different labels so that the program has correct information. Okay, let's get back into the main code. So that's about it. We released the temporary registers that we might have used for this operation. And this is the way up of the recursion, where now the result of the operation, where was it? Here. The result of this operation is now sort of returned back to this whole expression, which itself is a lazy procedure, and so on and so forth until we are out. Okay, so once the whole code is evaluated like this, we are ready to generate it. Now, one thing I skipped over is compile time execution, because there isn't really anything here in this code that does it, and I think compile time execution also deserves its own video. So for now, let's stick to the main, sort of the standard pipeline of the compiler. Okay, now we generated the list of instructions, or encoded bytes of the instructions, and we are ready to do something with them. We can either, as I showed you here, we can either write them into P32 Windows executable, or we can run them right away. So let's start with actually running it, because I think that is surprisingly a bit easier. Okay, that would be in program.c, I guess. Git, right. I need to look into here, right. So we have program.git, and as you can see, this is where the per platform things begin, because the way you would just-in-time compile something in Windows differs from how you would do it on POSIX systems, so Linux and Mac. We will look into the Windows version. For that, we need this, go to win32 runtime.h, and in here we need to look at this file. So we have a bunch of buffers, one for the machine code, one for read-only data, and one for read-write data. This is where we set up exception handling. I have separate videos on this, and it is a very deep topic by itself, so I'm just gonna skip over it. But the main interesting part is sort of happens here. This is the main loop where we are encoding sort of functions which are start and end. How's it called? I always mix up how is it called. It's not prelude. Sort of intro and outro of the function and each of the instructions. And they are all laid out one by one in this code buffer. Okay. And then we do the program patch labels calls, and this is going back to the instructions. So remember, in here we generated these auxiliary instructions saying to us where are the label locations in the instructions. So I know it's not very understandable probably. So let's say I have, where is my prelude? Yeah. So let's take something like this, right? So when I have a jump instruction, so I have jump and some kind of my label. This is what you would have in your assembly, something like NASM or something like this. The jump instruction is 0xE9. This is just the code for it. But then we expect it to have 4 bytes that tell us how far to jump. Are we jumping forward? Are we jumping backward? And how many bytes in the instructions are we jumping to? And this is what we need to figure out. So what this thing records is the position of these 4 bytes relative to the location sort of here, relative to the end of the instruction. Because in other instructions, you can have like extra bytes. So we need to record that 1 byte into the instruction, we have 4 bytes that are labeled. This is very finicky, and definitely took me like a day or so to make sure that this whole system actually works. But the point of it is that in here we can go through those labels, and we can figure out what are all their locations in the code, and we can write them down for each instruction. Okay, let's get back into here. Now we are saying to the system that the code is now executable. And we are also making sure that read-only data is actually read-only. I'm gonna skip relocations and starter functions. There are separate videos for both, so you can take a look at those, and they are not really very important for the main flow of the compiler. Okay, so now we've done the compilation. We have machine code. We told the operating system that this machine code is actually ready to run. So, well, we can run it. And this is exactly what happens here. We look up the entry point, and then we just jump to it like any other function, and we run it. And this is, again, what happens when I run this command. Okay, let's look at the other branch. The other branch is, first of all, let me say that the way this works right now is not how I want it to be working long term, but it is what it is. And we are doing this. We have another file called PE32C, which is implementing Windows portable executable format. That's what PE stands for. And it's actually PE32 plus, but you can't really put plus in the name, so I just stuck with PE32. And again, there are separate videos of how all of this works in more detail, but in general, it does more or less the same thing as the JIT, but instead of doing preparing it for the memory, it prepares it to be written out to disk. So it loads libraries, it prepares locations where the function pointers are going to be. This is all weird things about the libraries. Then there are stuff about how to handle exceptions. Again, this is also the same as you have in the JIT version, and it is very finicky Windows-specific thing. So again, if you're interested, I have another video on that topic. And then, same as in JIT, we are sort of we are preparing the instructions. We are calling the function encode here, as you can see, and the same thing happens in here. So it is sort of more or less the same code under a different source. For the labels, unlike the JIT version, where we do know exactly where in memory everything will be located, in here we use something called relative virtual addresses. So we're asking the operating system to do that patching of label for us instead of us actually doing it. Right? There's some stuff for permissions inside the code. This is an interesting quirk of P32 format, that you actually have to kind of sign it to make sure that the file wasn't tampered with after it was produced. It's an interesting algorithm, to say the least, but it works now. And here you can see that we have these 3 sections in the file. It's the code section, which is called text for historical reason. We have read-only data, and we have read-write data. And then we are just putting the buffers into those sections. And these are the headers of the file. Again, you can see more in the relevant videos as to how that works. And finally, we are just dumping that file to disk, and we are cleaning up some temporary stuff. That is a very, very, very high level overview of the compilation process. And again, I completely skimmed over any kind of compile time execution. I think, as I said, it deserves its own video, because there is a lot of intricacies there and a lot of interesting things. But for now, yeah, that's what I wanted to do. I know that was still a whirlwind tour of the compiler, but if I try to explain sort of more in detail each section, then it'd take forever. If you do have questions, I would be happy to answer them. Just, write a comment and ask for it. I'll either point you to a different video that is already out there, or maybe it's something I'm missing and I'll either answer it or maybe make a new video on that topic. So that's all for today. Thank you very much for watching. I hope that you learned a bit more about how the compiler is structured, and then see you next time.